for this function right here, we are going to find interval of decrease. Ooh, I think I went increasing. Okay, we'll change that. And find the interval where the function is concave up. So on this row, I've rewritten f of x with negative exponents, so it's easy to find the first derivative. Note that x cannot equal 0. It's not even in the domain of the original function. And here's f double prime. To apply the first derivative test, we want to know when does this expression equal 0. So that's negative 7 over x squared plus 16 over x cubed. Multiply every term by x cubed. Clear the fractions. And x is 16/7. That's your critical number, where the slope of the tangent line is 0. Here's the first derivative test. I put a little x on 0 because that's where the derivative is not defined, and actually the original function has a vertical asymptote at x equals 0. So there's two branches to the curve. To the left of 0, f prime is negative, so the original function is decreasing. To the right of 0 and before 16/7, the first derivative is positive, so increasing. And to the right of 16/7, like f prime of 3, the first derivative is negative, so decreasing. So here's the interval of increasing. The interval of decreasing goes from negative infinity up to 0. And we have to union that with 16/7 comma infinity. So this is your intervals of decrease. Test for concavity, very similar. Set the second derivative equal to 0. You get a hypercritical number of 24/7. We still have to include 0 to find out what's happening on the branch to the left of 0. Turns out f double prime of -1 is negative, so the original curve is concave down. Think when this is negative, we've got a frown. And similarly, between 0 and 24/7, the original, or f double prime is still negative, so still concave down. But to the right of 24/7, the second derivative becomes positive, so concave up. So at 24/7, we have a point of inflection. The interval on which the original function is concave up is from 24/7 to infinity. Note that we don't include the 24/7 in the interval for concave up, whereas for interval of increase or decrease, we actually include the 16/7. Okay, I just make a note up here that another way to do this problem is to rewrite the original function by combining all these terms, getting a common denominator. In this form, it's easy to identify the roots of the original function because that numerator factors into x plus 8 times the quantity x minus 1. And so the numerator is 0 when x is -8 or x equals 1. So part of graphing it, if you had to graph it, would be to graph the x-intercepts. Note there are no y-intercepts. So you could find the first derivative using quotient rule. I didn't make note here, but each term on either side of this minus sign contains an x. So you could factor out an x as part of simplifying that expression. It will look something like this. There's the x that I factored out. So I have another x times 2x plus 7, 2x squared plus 7x. I factored out this x, so I distribute a -2 times each term inside that parenthesis. So -2x squared minus 14x plus 16. That's the numerator. Still have that x to the fourth in the denominator. One of those cancels out. 2x squared minus 2x squared. 7x minus 14x negative 7x plus 16. There you go. And you could do g double prime in the same fashion. Notice that this is equal to 0 when x equals 16/7, just like we got over here. Okay, there's what the graph looks like. There's the function increasing all the way up to an x coordinate of 16/7. And this is the point of inflection where the concavity changes to concave up. It doesn't look that much up, but the slopes of the tangent lines are increasing there. There you go. Hope that helped. If you have any questions, post a comment.